We live in the golden age of silicon. In just 60 years, we went from the computers the size of room that could barely do math to having the entirety of the human knowledge in our pockets. But there is a secret that computer scientists know. Our computers are actually kind of dumb. There are problems out there in medicine, logistics, and cybersecurity that would take today's fastest supercomputer billions of years to solve. We hit a wall. To break through that wall, we don't need faster chips. We need to rewrite the rules of physics. We need to enter the quantum realm. Today, we are explaining quantum computing. Before we get to the weird quantum stuff, we need to understand what we have now. We call our current tech classical computing. At the core, your phone, your laptop, and the internet are based on a very simple idea, the bit. The bit is a switch. It is either a 0 or a 1, which is a 0 or 1 off or on. That's it. Everything you do digital, reading, watching Netflix is just billions of those tiny switches flicking on and off very quickly in specific order. Classical computers are amazing at linear tasks, doing math, storing databases, following a recipe step by step. But they are terrible at what we call exponential problems. Imagine trying to find the best route for a delivery truck with the 50 stops. A classical computer has to check almost every possible combination one at a time to find the shortest route. Add a few more stops, and the time it takes to calculate explodes. It becomes impossible. Quantum weirdness. In the early 20th century, physicists realized that down at the microscopic level, the level of atoms and electrons, the laws of physics we know break down. Things get weird. Quantum computers replace the bit with the qubit, quantum bit. Like a normal bit, a qubit can be a 0 or it can be a 1, thanks to the principle called superposition. So it can be also be a mixture of both at the same time. Think of it like flipping a coin. Classical bit is coin where when it lands it's heads or tails. A qubit is a coin while it's spinning in the air. Is it heads or tails right now? It's sort of both. It has probability of being either until you catch it and look at it. Why does this matter? Because a classical computer has to look at the problem one path at a time. A quantum computer, thanks to the superposition, can look at all possible paths at once. If superposition wasn't weird enough, hold on to your hats for the concept number two, entanglement. Albert Einstein called this as a spooky action at a distance and it really bothered him. In a quantum computer, we can link two or more qubits together so they lose their independence. They become a part of the same quantum system regardless of how far apart they are physically. Imagine having two magical dice. You leave one on Earth and take the other to the Mars. You roll the Earth die and it lands on the six instantaneously faster than the speed of light. You know the Mars die also landed on six. They are linked. When you combine superposition, being in many states at once, with entanglement, linking those states together, you get a computer that grows exponentially powerful. With just a 300 perfectly working qubits, you could represent more states simultaneously than there are atoms in the universe. That is an unthinkable power. Quantum computers aren't meant for checking email. They are specialized tools for specific impossible problems. First, chemistry and medicine. Nature is fundamentally quantum. Molecules don't follow classic rules. Right now, trying to simulate a complex drug molecule on a supercomputer is like trying to build a Lego set with a oven mitts on. A quantum computer can simulate exactly how atoms interact. This could lead to breakthroughs in battery technology, material science, and discovering drugs for diseases like Alzheimer's in months rather than decades. Second, optimization and AI. Remember the delivery truck problem? Quantum computers could revolutionize the global logistics, optimize financial portfolios instantly, and train AI immensely faster than what we do today. And third, the scary one, cybersecurity. Almost all internet security today relies on math problems that are too hard for classical computers to solve, mostly factoring massive prime numbers. A sufficiently powerful quantum computer using something called a Shor's algorithm could crack those codes like a walnut, and it launching a race for quantum proof security. So, if these things are so amazing, why don't we have them yet? Because qubits are incredibly fragile. They suffer from decoherence. The slightest vibration, a tiny change in temperature, or a stray electromagnetic wave causes the qubit to lose its quantum state and collapse back into the boring old pit. To get them to the work, we had to cool them down to the near absolute zero, colder than the deep space, and shield them in a massive vacuum chambers. And even then, they are currently very noisy and error prone. We are currently in the vacuum tube era of quantum computing. It's messy, it's expensive, and it barely works. But 70 years ago, so was the classical computing. We aren't just building a faster computer, we are unlocking a new way to understand the universe and using it to solve the mankind's hardest problems. The quantum revolution isn't coming, it's already begun.